So I totally apologize. I was running a little late. I'm in laptop update hell. I don't know if you've been in there before, but it's like one update screws you with another one, screws you with another one, and a couple are mandatory by DePaul. So I can't do that at home. So we're recording. All right. PA5 Basics 5 questions. Yes.
I mean, mine are all about the optimization, about the benchmark one.
So the way to do the benchmark stuff, at least the way I approached it, is my release is my kind of I literally run the release and I cut and paste that result into a text file and just keep it in my hand so that I know what my numbers are. Because I don't want something like I switch around with the fast option. What was it again? You know, so I print my release off so I have a reference. And my goal is to try to beat those numbers. And so I kind of scan through the options and I start flipping the options and trying them and seeing if I can understand just by their terminology what they are. And I tend to do one at a time. I know it sounds silly, but I start to dunk, 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 dunk. And then I'm like going, this seems interesting. And then it will give you a little warning. It says, you also have to have this flag, or you can only be in this mode when this one's on. So those are combos. And you just start to experiment. And when you get a speed increase, you leave those buttons there. And if you have a button that says, I flipped this on, I flipped it off, like, you know, you flipped in like, I don't know, whole program optimization. Like, wow, that's a keeper. Then you start changing something else. And you're like, okay, you know, I'm not going to screw that one because that one gave me a jump. Now, did it jump all those metrics? No, it might have only jump maybe math or maybe just the memory one. But as soon as it does it, I keep it and I keep going after other ones. And I don't know a better way. Now, I do think, and I pitched this to a lot of students because I think you guys can do this right now for the students who've taken neural networks in training. You can hit every option programmatically. I run my unit tests by launching the compiler and debugger from a command line. So I write Python scripts that run that. Well, that means you can have a file that has all the different flags. So you could, in theory, say, here's my code, and just let it cook for 2 days, and it goes, and here are your options. Right now, not just for this assignment, but I think it'd be kind of cool just in general if somebody had that tool out there and saying, I have my program, what are the best options and settings just to make it faster? Who cares about the rest? But now you need something that has metrics, something that has a time on it. As long as your program has a time, this way you know you're doing better or worse. Feed that back into your training system. I think that'd be kind of cool. Problem is, I just don't have time to do it. But it sounds like a really neat master's project, master's thesis. Hell, you can publish that. You can go do it as a side and then go get $300,000 starting salary at Microsoft. I mean, there's a lot of different things you could do there because I think that has real world return. Right? So that's my approach. So I don't know, do you have a better approach or anybody has a better approach? I mean, it's kind of brute force.
I mean, you could.
The good news is you can run it and watch TV. So it's not. Let's keep watching TV.
I mean, really, you can. Yeah, it's more of a like, okay, click a button, hit run, wait 5 seconds, click a button.
Are you sure it would finish in 2 days?
No. I'm talking about the neural training might take, I don't know, who knows how long. But I'm saying for you can be noodling with some of the options and be watching TV.
The other thing what you could also do is turn one on, turn that one back off, turn the next one on, turn that one off, and to see how
if they're linearly independent.
All right, but there's some that you'd have to turn multiple.
There's some that are interconnected. Like if you're in this mode, these other ones will just get kind of just negated because this one damn flag is on. It kind of breaks the rest.
All right.
I at least what I found was like, and then to turn this one option on, I had to turn in 4 other flags, and like I did all this stuff, and there wasn't much of a return. So like. Things. So I think release does a reasonable job to catch us. Can we make it just a little bit faster in some of those areas? All right, other questions on proxies, RVO. And I think it was prevention of implicit. You know,
Just grading, I'm wondering, like how would it be graded for this assignment at the very least?
this is some, I think, it just, I'm trying to remember how it went. Yeah, here, let me see. I might have my, I always do the assignment and then I grade myself. This way I can test my grader. Because I don't trust them. Bam. Winter was last time we taught this. Nope, the other students. Yeah. 5, right? So I run everything 3 times. And I take the best time. And run the benchmarks. So I'm giving you points for the RVO, 2 points, so speed, 4 points for proxy, 2 points for the benchmark, and then 2 points for your errors. So
Just the benchmark math.
no, I look at everything, but you know, so I break it down. We'll see what the numbers are because different machine, so it's all gonna be different, but so essentially it's all gonna be time-based. And so where you kind of lightly on that. Good question. All right, and then for there's something I was gonna say. I'm going to be grading PA4 and Basics 4 tomorrow or tonight, you know, they kind of blur into each other. All right, so no more questions on that stuff? All right, so this new stuff we're doing now is called SIMD. And kind of set the stage for SIMD. All right. So SIMD is single instruction, multiple data. And the whole idea is that this is what makes things really fast. So you have essentially, you know, here's your CPU. So let me go way back in the day. I'm gonna go really far back in the day. There's this thing called a 386, right? And it was a processor, and they had next to it a 387. And the 387 was the math portion of the processor. So if you got a 386 DX, you got the math on it. If you didn't have it, you would have the SX, which we lovingly refer to as sucks, right? And so what they basically do is kick off to this little processor to do the floating point multiplications and divides, right? Fast forward now, you got some Intel i5 or 7 or whatever you have, right? And hanging off of this is this single instruction, multiple data. So it basically is a coprocessor that sits off of it. And what it can do is do 4 multiplies together the cost of 1 multiply. So instead of you multiplying A times B, and you get some answer here, right? You can do A0, A1, A2, A3, B1, B2, B3. You can do all these 4 multiplies and the cost it would take you to do 1. Right. So suddenly you're boom 4 times faster doing this stuff. The catch is for this to be used, the moons have to be aligned correctly. So your data has to be in alignment. That's why we emphasize alignment so much. And you have to use these special instructions, right? So this portion here is a little bit rougher, but it gets you really, really high speed things. So like if I was in the high frequency trading, anytime I'm doing any math operations, I'd be doing SIMD. If I'm doing image processing, game development, SIMD, because we are going to use this stuff. So imagine you have a car and you have a second engine, a turbocharged, but you don't turn it on. So everybody bought the turbocharger. It's sitting in your PC right now, but almost nobody uses it. So to kind of get us idea on speed, we have a couple movies, of course.
The
Flashcards und jetzt stapel ich sie auf. Flashcards, yeah. Abbauen, immer schneller abbauen, yeah. Stapel ich sie auf und stapel ich sie auf. Down, slack, 1, 10, 1. Riesen Pyramiden
Did anybody do this? Oh, really? Okay, so it must be a generational thing.
Yes, it was very much so.
What did you think? Coordination? Like, I like cuts.
It's gonna be a tournament-based thing. Like,
Yeah, that's the-
it's like they play it in big tournaments. If you ever get to pass, it's pretty interesting. When you actually like watch people fast, they're insane with it.
Right, so that's where I'm going with this. So then,
Super Hands presents Emily Fox.
so I mean, like, so I'm like, oh, that's pretty fast. You know, again, trying to find videos that's convey fast. It's kind of hard. So then I'm like, going, can anybody beat Emily, right? Because Emily is kicking butt. And I did find one, but I'm not sure if it's prudent.
I think you got it.
So, I think you nailed it.
377.
Yo.
Oh,
All right, but I didn't know this thing existed. All right, so then I'm looking more and more. I'm like, all right, come on, we got to find more things that convey speed. So I'm just scouring the net, finding things I probably shouldn't find. And I came across this is some game contest show, and they're drinking fluid out of a jug, and the technique was amazing. And so I know, a lot of you are in college, you might have contests. This might be a cool contest.
秒で半分飲んでて止まってますからね。この渡辺克也の11秒65って驚異的な記録を抜くとしたらさっきのあの半分。
So he has a record at 11 seconds 65.
しかし飛び散らせたらまた NG ということ
That was like a leader.
どうでしょう。
Peter actually has like
Just water or is it carbonated?
Who knows what it is? I don't know.
This is very.
I assume they color it so you can see it.
oh my god.
I think in order to do that, you have to literally just open your throat and let it all flow down.
So the technique was amazing because what I think he did was he force pushed it out the nozzle. Now we all know, but if you took fluid mechanics, you would know this that doesn't change the speed. It's mass flow rate, which is the size of the diameter. But he holds it in his mouth. The empty is there. He's still swallowing, right? So he's totally like hiding half of like a couple seconds there of like game there, but he clobbered it compared to the other guy. So I was impressed by the technique. So that was. Let's try the technique again. If I'm in a contest, this is the trick I want to do. He's still swallowing. So basically spend time on the internet, this is what you find. All right. So then, so CPU is like single operation, right? And the SIMD is, we can do 4 operations. And if you use this more advanced SIMD, you can do 16 operations at once. But if you eventually keep staying with optimization, you get into parallelization where you get multiple processors working together. And nothing really beats GPUs. GPUs is like just a ton of processors that can be run in parallel. And so this kind of gives you an idea of parallelism, right? So this is from the guys who do Adam and Jamie do this show where they blow things up. I forgot what it's called.
Paint a picture for you guys in a way that a CPU might do it, as a series of discrete actions performed sequentially, one after the other. This paintball gun is an XY servo-driven bot that will readdress itself with each pixel that it has to lay on this canvas right here. 2, 1. Let me start again. Underneath this tarp is thousands of pounds of aluminum and steel, a mile of high-pressure air hose, hundreds of pounds of compressed air, and 1,100 specifically addressed paintballs in 1,100 barrels. Ladies and gentlemen, Leonardo. Turn it sharper. Sharper. Even sharper.
Watch out.
We gotta get so the whole audience can see it. Come on, let's go forward. Oh.
So that's GPU, it's a little bit over larger than this, but you get the idea that we're gonna be doing things in parallel. So when I started teaching this material, we're gonna learn about intrinsic, SIMD, and stuff like that. I would talk in the hallway, and a lot of people are like, "On who's this SIMD thing?" You know, and I'm like, "No, it's SIMD." You know, my Chicago South Side dialect is kicking in. So it's SIMD, single instruction multiple data. So we're gonna go through this and kind of understand how this works. It's pretty cool. Seriously, many people don't do this, but you bought the processor, it's sitting there, might as well turn it on, right? So intrinsics, right? Intrinsics are these little compiler fragments. And what they are, basically, instead of writing assembly code, if you write assembly code, the computer hits that line of code and says, all right, I will do what you say. And the problem is, when the computer does optimization, they move some code up a file, down a file, rearrange it, delete it. And so as you write assembly, you actually slowed the processor down. There's no net improvement from SIMD, from assembly. And so what you do is, click on this, right? You basically have this thing called compiler fragments, macros. And these little compiler fragments is machine code, but they have little dirty flags for saying, I use these variables. I have to be done before this. And it has these little hints in there. So then the compiler looks at this assembly snapshot and they can move it up and down and reduce it and even undo it and rework it. So it's like an inline but it has knowledge, so it can gives hints to the compiler of how to optimize, how to shuffle stuff around. So this code is actually inlined. So when you use an intrinsic property, it gets inlined right into its place. It doesn't call a function. So that removes all the overhead. The intrinsics are written by compiler teams. If you have a need if you ever feel the need that you want to type assembly, you contact the compiler group and say, this is the problem I have. They're like, oh, here's our list of unpublished intrinsics. We have this one done already. Here you go. And then if you make a compelling reason, they'll actually create one for you. But they have to write it because they have to put internal hooks to make it work with their compiler. So the GCC team is different than the Microsoft team, which is different than Intel team. So you have to kind of contact the compiler teams. It's really fast, and it's really interesting little thing. So this little snippet of code that you slam in there, it just works, and can also then later be optimized and rearranged by the compiler. Right? So there is a lot of black magic in the when you look at an assembly code. And I know for those of you who've taken the systems class, you did a little bit of assembly, but the way the assembly really works is much more different. You guys we're working on this like kind of baby subset of instructions. The full instructions have branch, not equal, underflow, speculation, move, root. Sit there says, I do a comparison. I'm supposed to jump down to this line of code and we'll execute it. But just in case the comparison is wrong, I'll start executing. So it executes two pathways. This is what our compiler does right now.
Yeah.
And he goes, answer, and it throws away A or B. And so when you do this, you have this timing and delays and schedules. Then you have a branch, but then the two lines below the branch code will always get executed. You're like, but there's a jump. You're like, yeah, but these two are in the delay slot and they're executed automatically when you call this function. And some functions have branch that won't use the delay slots. So it's a nightmare to try to piece together timing rules and consistency rules to kind of get this working. So instead of you trying to figure out, you write using these intrinsics, intrinsic has a hints, those hints go to the compiler then honors those and shuffles things around so it still optimizes the timing. There's a lot of these intrinsics that are built in the compiler, and we just don't even know they're there. So a side note, what is the most important equation a compiler group or a processor group would write, math-wise?
Quadratic.
No, thinking lower level to that.
Addition.
Like, well, addition, subtraction, multiplication, right? They got all those.
Yeah.
But then the next level is like square root function,
Right.
sine function, stuff like that.
Yeah.
So how do they make it a square root function? It's really interesting. I used to have to write my own square root functions.
Assuming they do the Taylor expansion.
No, that would be horribly slow. But that's how we would do it mathematically.
Yeah.
Right?
Do they like just
So
take
there's
like
papers
half
there.
of what the value was, just
There's papers that are built on how to make these functions fast, and they actually get special opcodes for it.
Huh.
So when you do a square root function, they actually implement this function. 1 over the reciprocal square root. You're like, why? And there's tons of papers. There was a lot of papers that will show you how to do this faster and reduce the math and really interesting kind of ways to get there. And then then suddenly competition started to get more and more fierce. So now Intel says, you know what, you're not allowed to publish anymore. And then IBM's like, oh, no, don't publish because we have on our servers at a disadvantage. So then all of them, they all have their own secrets at each company. So they further expanded this, but they write this function. The reason for they write this function is if you do x divided by square root of x, right? So this is x to the 1, x to the minus 1/2. This is x to the 1/2 or square root.
do the same thing.
right? So this equals square root of x, right? If you do 1 over square root of x multiplied with itself, is equals 1 over x. So it turns out this is a really, really important function, right? And so they try to optimize the snot out of this. When you look at sine cosine functions, right? Oh, that's not actually bad, Ed. All right.
Yeah.
You see symmetry. So if you take this into, divide up in quads, this part here, if you negate it, you get this, right? If you mirror it, you get this one, and then if you negate the mirror, you get that. You get that one. Right? So they'll focus like mad on just that arc. And I remember in the old days, we used to do piecewise estimation of that arc. Because if you do it, then you do the couple symmetry things, and you can get any point on there. And if you can get sine, you got cosine, you got cosine gets sine because they're only out of phase, right? And what they do is they'll actually have an opcode. It's like, like sine seed, and it does, and it kind of gives you that arc. Then it goes boom, 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 mirrors it. It's like, here's your answer. So it doesn't even do the traditional, Taylor series approximation that you would learn in math class, because we're just worried about how many cycles it is, right? So the compiler teams are doing this, and it's been evolving. It's been pretty crazy. And so there's some intrinsics that are built in, square root, right? But we have these as well. Here's your sine function, your sine f, right? Your hyperbolic floating points, right? Your square root f, power function, which if anybody uses power function, you have to really ask yourself why. So power function is implemented. Power function, a lot of people are like going, hey, x, oops, out doing that crayon level, x squared, right? I can use a power function. I can say power x2, right? And you get the right answer. The compiler, a power function is way more complicated than that, because you could say, it's really generalized as x raised to the y, and these can be decimal points.
Yeah.
Right? So you got, 3.215 raised to the 0.115, right? Then you're like going, how the hell do I do that, right? And then you find yourself doing natural log over natural log. And it turns out that's a slow, it's a crappy one. Even with all the tricks the compiler does, the compiler teams haven't numerically found a better way to do natural log. But yet natural log is like everything.
Damn.
So if you use the power function, you have just, decided that I want to go from a sports car to a big wheel, and you want to drag a tank behind you, in gear, and you have to drag it through the mud, right? So it's really, really slow. Make a question?
What's the difference between arctan and arctan2?
Well, first of all, look it up, right?
Sure.
RTFM, but basically you can control, I think there was an extra parameter in there. Yeah.
So all the others make sense. I was like, okay.
So arctan, I think you just put the result in and tells you the arctan. Arctan2, I think you put both the X and the Y component.
And it tells you.
And it'll give you it's been a while. First of all, if you're using trig, you're probably messed up. The reason I say that is almost every real problem that you find yourself needing trig functions, you don't know your vectors well enough. So dot products, cross products gets you in normalization, gets you through a lot of problems And if you find yourself using cosine sine, you're like, I like this luggage that I learned in high school or grade school called trig. And I want to keep using the same luggage with me when there's these things called vectors that are a lot faster. Right? All right, so these intrinsics are built in, but they're built in underneath it. So these are actually intrinsics we're using right now. All right, so 64-bit processors came out, and they realized with the 64-bit processors, most of the programs people were using were only 32 bits. So you got this 64-bit data set, but we're only using 32 bits of this when it first came out. So the question is, what can we do with those X? How do we use the 64-bit machine? Because most of the time we're not a 64-bit. Just a reference point, we went to the moon on 16 bits, right? 32 bits is amazing. 64, I don't even know if you can quantify this, even more ridiculous. The catch is, once you go to floating point numbers, you already added blur to your camera. You added noise. Did I do that whole adding an offset loop with floating point number? Do we do the floating point number verification here?
I don't think so.
Okay, let me give you this real quick because this is worth it, and then so what every scientist should know about floating points, is that Rainbow or no? Okay. I do this a lot, and this should be taught in systems, but they don't listen to me. All right.
Yeah, they basically go, floating points are complicated, and then they move on.
Oh, really?
Yes,
Yeah.
that's literally what happened.
At some point, we should all go out eating and drinking, and you can give me the dump so I can have ammo to go after people with. All right. All right, so here's floating point float, x equals 0.0f, 4 and high equals 0. I less than, we'll say 1,000. I plus. All right, so simple enough, pretty mundane, right? We're gonna loop through there and print out. I'm using print because print is faster than trace out. Here, put a breakpoint there. Right, you can see that it starts from 0 and then it gets up to very close to 1, right? And if we do this, I hope this thing holds the property here. Yeah, okay. So now let's just add, that was close to 1, so add 3 more zeros, should be close to 1,000, right? And this thing's gonna cook and cook and cook and cook. All right, so now we're like, okay, this print's gonna take forever, so let's kind of stop that and let's do this. If I modulus 1,000 equal 0. And that's my order of precedence, so I'll put parentheses around. Right, so here we go. Getting close to 1,000, right? So let me just let me lower the number down a little bit here. I'm gonna add a couple zeros here. And that should just lower it down. All right. So here, 99. And now I'm just gonna add 2 more zeros.
It's gonna be so.
256. Right, now if I add 2 more zeros,
Numbers. But this is how
Right.
numbers work.
it'll be 256.
But it's perfect, you these.
And well, no matter how many do, so I'm adding more, right? So the reason I bring this up is floating points and approximation. And what you should study, especially if you're doing anything with programming for a living, is there's a reference called what every computer scientist should know about floating point arithmetic. There you go. And so this is like mandatory read. And so you should start to, you have nothing to do and you want to read about IEEE floating point notation. This is it. And this talks about how it works. The catch is when you add a really, really small number to a really, really big number, the result has to be a big number. And so it's like you have an elephant, you're adding a feather to it. Well, but you have to sit there, okay, how much does the elephant weigh? It's like, weighs the same. Yeah, but I just added one feather, like it still weighs the same as the elephant. But if I keep adding 1,000 more feathers, it goes, still an elephant. It just ignores it. But what if I do 1,000 feathers times a couple trillion or gigaplex? You're like, okay, eventually that many feathers should change the mass, right? No, it doesn't, because when you add one feather to the elephant, you get an answer. And it can't accumulate it because we have different magnitudes. So only thing that's true in addition is fixed point integers. As soon as you go to floating point, it's like you're rubbing your eyes and you're looking at the screen, right? It's blurry. So the question is, a 32-bit floating point is an approximation. A 64-bit is approximation. Just a more costly, expensive approximation, still approximation. So once you understand that, you start to understand numerical methods and understanding that you can do a lot of your math in single point precision. And if you understand magnitudes and differences of magnitudes relations, you can understand how to normalize this into the appropriate calculations. Think about it, they made it to the moon on 16 bits. We have 32, which is just silly, right? We went from 16 bits is 64K of space to 4 gigs. And now somebody's saying 4 gigs is not enough, you need 64-bit. Like, what? So you can, so this is a good thing. I'll send a link on this stuff, but I just want to show you that floating point numbers give you trouble. So this is why when we moved to 64-bit, people said, wait a minute, we're spending all that extra cycles to do a double times a double. And it's like going, we don't need that precision. We don't have that dynamic range that dictates that. So they're trying to say, what can we do with that other bits? So they came out with some new instruction sets, right? So this all happened somewhere in that ballpark of 2005. So in the early days, this is where I started. I was on signal processing, digital signal processor. So this is for like telecom, so telephones and all this other stuff. And they had this in the 1980s, a DSP processor. And they also had, the big ones were the TIs, the Texas Instruments that came out in 83. And they were just trying to do multiply and accumulate, so multiply 4 things and add them together in 1 or 2 cycles. And so this is 1983, right, in 80. Well, so Intel, not missing a trend, came out with theirs in 1997. So 17 years later, they said, this parallelization thing sounds like a good idea. And they were actually reacting to a leaked paper that came out of AMD. And AMD started doing 3D now. And so they're both moved to 64-bit. It's like, wait a minute, we can do two floating points at the same time. And that started this SIMD thing, right? So the first thing was MMX. MMX is basically takes the 64-bit data and we chop it up. We chop it up into one 64-bit, or we can say two 32-bit integers. These are all integers. Or we can do, you know, 4 16s or 8 8s. And now we have one register that can hold multiple fields. Well, as soon as we can do that, we can have special instructions. So here's the instructions they had. And the MMX instructions were mainly geared towards routers, geared towards printers, where you had data that's misaligned. And so like it has swizzles and shifts and packs and masking. And that allows the processor to extract the data a little bit faster. So this wasn't that useful. It did do some integer-based additions and stuff like that, but they were all like adding 2 bytes together to get a byte. You know, like, you know, okay, cool. I guess that's cool, right? And this is how you would do it. You would actually have to write a machine code directive and do that. So there's your MMX registers, anything with the MM in front of it. And so you know, here's an additive one, right? So when I see this stuff, I totally like going, please no assembly. You know, I did enough of years of therapy to get out of my assembly days. Nobody else should go through that hell. It's really, really medieval. So besides that, the assembly stuff, we have the MMX, which is all just integers, and it's not that useful for us. So later came out SSE. And this is where I think the cutest part of this lecture comes into is the naming convention, right? So SIMD stands for single instruction multiple data. So this is SSE, streaming SIMD extensions. So like inside the acronym is a abbreviation of an acronym. It's kind of cool and recursive in a weird, sick way. All right, this came out in 99 and they added 70 more instructions. And so what they did is they expanded it, saying instead of 64-bit, let's expand it to 128-bit. So they have 128-bit, and what they did is they sat there and said, we can look at this 128-bit as 4 floating point values. So they only have 8 registers here that they added, but each register can hold 4 floats. And of interest to us are the functions here: add, subtract, multiply, divide, and you see PS versus SS. So one means packed scalar, the other means single scalar. So some other instructions here. How to use this was, again, you had to do assembly. So this is some old code that I wrote. So you do the assembler directive. And so here's your MMX, XMM instruction sets. And here's the payout. You do this whole thing is like, and there's the multiply. And there's shuffling and wrapping and stuff like that. Right? Well, then they basically, if you kind of go down to one simple function, this is a vector times a scalar. So basically we take a vector, which is, you know, X, Y, Z, W, and then you want to multiply it by a scalar, we'll say A. This becomes AX, AY, AZ, AW, right? So this is how you would do it in assembly. And it turns out, you know, here we are again, we're writing assembly. The compiler can optimize it. It stops when it hits this, it does the exact work. But they came out then with intrinsic functions. And the intrinsic functions are these little macros. So you pass in the variable, and it will do this macro. So these two code bases are exactly the same. And the difference is the one in blue has these intrinsics macros, and they can be optimized even better by the compiler. So not only are they doing the same things, the blue is going to be way more optimized because it can shuffle stuff around and move stuff around.
Are these part of the language or part of the? Okay.
Yeah, this is part of the Intel AMD standard. If you switch to ARM processor, there'll be different instructions. So I'm talking about this part right here, macro. Right. So which one did you like? You know, I've said it's easier to look at the macro ones, right? The intrinsics look a little bit like C code, right? Here's old PlayStation code that I wrote a long time ago. And you know, here again, it's assemblers with loading it, adding the vectors up and writing it out. So I'm adding two matrices together. And then what Intel did, PlayStation is they started saying, oh, you know what, instead of you writing this, you can write in a higher level language, and they had a compiler that compiled your language into some intermediate, which generated this. So even Sony realized writing assembly is really burden, it's hard, it's confusing. And the reason I say that even Sony never helps you out. Yeah. So Sony is a very hard program platform to work on, right? But here's the catch. You need to have your data be aligned. So you have to work on your data, it has to be aligned to 16 bytes. So you have to use this declaration spec in the align macro. So here's an example, a declaration spec align 32, this structure would be aligned to 32 byte alignment. And it's alignment that we know and love. Well, who wants to type that whole mess every single time you want to use something? So you sit there and say, oh, well, I'll just put it as a macro. So you put it as a macro. Now you have to put the word align in your structure or your class definition, right? And you have to do this even with a float arrays or whatever. So it turns out this alignment directive seems to be problematic. So the compiler guys decided to improve, and they decided to give you a built-in type. And this built-in type is the underscore M128. It's 2 underscores. Underscore. And this is defined over here. And what's unique about this is it has it as a union. We'll talk about unions in a second. It has a declaration spec of the intrinsic type. So this is going to be 16 byte aligned. And you can access as groups of floats, integers, or shorts. Does everybody understand how a union works?
I never got a formal description of it, but I assume it's basically telling the compiler to basically put these variable or tie these variable names to the same section of code, the same section of memory.
Same section of memory, correct, yeah. So you bought some space and you can say, I want to read it as if they were 4 floats. I want to read this as if it was 8 shorts. I can read this same space as if it is 16 bytes. So let's do a union. A union so you have this one chunk of memory here, right? And this union says, what's the size of this? The size of any who's the largest? This is 4 bytes. A short, but there's an array of 2 of us, so that's 4 bytes. Or a character here is literally 4 bytes. So this thing is 4 bytes. So we'll have this bit patterns here, right? You know, 1s and 0s. Just imagine they're all filled in. And the question is, how do we look at that data? How do we interpret that data? So we can sit there and say, you know what, if we just read the whole thing, we can call it X. If we wanted to, we can read the thing, that same memory, and the first one is S bracket 0, next one S bracket 1. Or we can read it as literally so character 0, character 1, character 2, character 3. Right? So this blue here, how do you want to read those bits? So if you read this data, right, and you go data dot x, you're reading it all the blue bits as if it was an integer. If you do data dot s1, you are reading just those 16 bits as a short. And if you did, data dot C1, you're only reading that much, those bits, and you read that as byte.
Is that backward compatible to C?
This is in C.
This is C?
Yeah. The compiler doesn't like it because it's very easy with intrinsic types, right? Intrinsic types are integers, floats, doubles, anything that is built-in type and has no constructor. So an integer doesn't have a constructor. But if you create a class, call it dog, and you have an integer in there, well, now, even though it's still an integer, it has a constructor, so it's not an intrinsic. So on intrinsics, this is really easy. So in the old C days, you only had intrinsics. So boom, 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 you can do this stuff. In C++, it kind of gets crazy because what if you had a union like this? Union. And you had dog, cat, bird, right? Each of these have constructors. And so when you initialize data that has a union, the C++ compiler goes, holy shit, we're in trouble. Which constructor do I fire off? I know you can access the data by just going data.c and you're getting a cat. But cat wasn't, the constructor wasn't called. So in unions in C++, there's a big warning that they'll spit out at you saying, warning, the constructors aren't called. That's part of the spec. So it's just the data storage. So so a lot of times you'll see unions in C++, a lot of people don't use them. You get this warning. So a lot of times we just press the warning because like, yes, we get it. That's how they work. Thank you for telling us, right? All right, so why is this important? Underscore M128 is a union. And one of the things in here is a float F32 bracket 4. So it can be used as for floats. You can also have it as int, I32 4. So you have a lot of choices. So this underscore M128 is this union over here. So that this data, and this data is, here it is, it's 16. So here's 4 bytes, 4 bytes, 4 bytes, 4 bytes. The whole thing is 16 bytes long. You can read it in a number of ways. So maybe the correct way to draw this out is the whole thing is 128 bits large. And if you want to read it as floats, you get 4 floats. F0, F1, F2, F3. Or if you wanted to, you can read it as 2 unsigned int 64 integers. Right? So however, whatever dot you use is how that data gets interpreted. Right? Now, so why do we use this data? I love this because somebody did all this work for me. I don't have to do this again, right? So what I propose, and I started this 20 some years ago, is to take that data structure and make it a union with my data structure. So here's my class vector. It has 4 floats. I make it a union. So now it's a union with the top one, which is M128. It's a union with the bottom one by 4 floats. So the union size will be the size of the biggest guy. The top one 16 bytes, the bottom one 16 bytes. So the whole size is 16 bytes. By having this as a union, I get all of the alignment here. This adds all my alignment crap in there. So now the compiler goes, oh, thank you. This has to be aligned because somebody might go .m, so therefore the data has to be aligned. So the next thing is, normally you give it a name, union data. Then underneath the hood, it'd be union, if you go data.m, you get this first line. But then the structure should have a name. So let me give these names here. Data, and we'll go at the data. Right? So here's a proper name, here's a proper name. So if I want to get M, I just go data.m, this data.m. But if I wanted the Y component, it'd be this arrow data dot v data dot Y. And that feels heavy, right? It doesn't do anything. So the compiler kind of complains a little bit, but if you have unique names here, if everything has a unique name, it can infer and deduce this. So now I can just go this dot M and get the M, or this dot X and get the X. And so I have an anonymous union with an anonymous struct. So this is how I would access the data. I just type in vector A and boom, I get the __ M built into it. So it's aligned. And now when I want to access the X, I just go A.X or A.Y. And it feels very natural. If I wanted to get as an M, I just go A.M. So the union with anonymous gives us this clever trick, right? And this is going to make our coding look a little more English and a little more easier to use.
So the anonymous pieces in there are like it's like a 2-layer, like a almost like a class nested in a class, except you don't use the name of the
right. So
middle.
So the compiler's always trying to like it. The compiler's very nice. I think it's more nicer than I would be. It said, you know what you wrote is correct. I just got to figure out what you mean. So it goes A, like cool, that X, like, okay, that's M. Oh, I found X. I guess you mean that one. So it will infer that as long as those names are unique. Otherwise, you have to give that whole dot data dot v data dot X. That's the proper full name and length. So it's kind of like here. Everybody at the party is part of the optimized party, right? And then you have, Keenan, right? There I am. So I'm dot M. So optimized party dot Keenan. right? But you're like going, well, what are you? And it's like going, I'm optimized party student dot Jeff or dot Lisa. And the catch is like, if there's only one Lisa or is there only one Jeff, do we really need to say optimized because they're in the room? Do we really need to say student? Well, they're not Keenan, so that by definition, it's somebody else. So we can infer that and deduce that. So the compiler complains a little bit because it's like, we like you to use name structures and name unions. I just like, yeah, whatever. I'd rather have easier code to write. They do the same thing. There adds no delay, no speed difference. It's just nomenclature. You want the code to be easy to use, otherwise people won't use it. So does that make sense? That it's trying to solve it. It's because if you had a function in your base class and in your drive class you call it, it goes, I can't find it in my drive class, I'll go up a level. Oh, I found it. So the compiler is always trying to solve what you're trying to do. It's trying to remove trying to figure out the mapping and remove the ambiguousness. Now, if you call a function and there's a function at that level, and you also have a function with that name, it goes, which one do you want? So now it's ambiguous, right? And that's where, did you mean to overload it? Did you overwrite it? Do you want to scope to the base class? So you have to kind of give it more of a full name.
And these are, your example there says it's a class, so it should be private by default, but
Well, no, yeah, I didn't put all the stuff.
Oh,
here.
okay, so there's more. Okay.
In public. What the problem is, I used to always put the word struct here. Then I was like, what's a struct? I'm like, I don't want to get in that religious war. Yeah, it's just inside your code, anywhere you can do this. Or if it's public, you can use that externally. All right, so here's your data. And here's the 0 to 128, the X, Y, Z. And it's weird. In the book, sometimes it puts 0 at the right side, sometimes it puts 0 at the left side. It doesn't really matter. So here's literally a screen grab from the editor. And you can see that here's our definition, the .m, and then here's the XYZ. And then here's the .m, when you expand it, you'll see, if you look at it as a float, you get a 1, 2, 3, 4. So this stuff was really nice and it's laid out well, and the debugger will even handle the aliasing well for you. So we'll see in a second when we start coding. All right, scaled versus packed. So there's two different types of data. Scalar, which is the only one element. So even though there's 4 spaces, we're talking about space 0, the first location. And then we have packed. So it'll be SS for single scalar. We have packed, which is all 4 elements are jammed together. So it's parallel scalar is what they call it. What's interesting, they also describe it as packed data. I'm not sure if which word they're trying to use here. I always think of it as packed, not parallel. So the way this works is, if you're using _PS, you just, here's your A, and here's your Y. I mean, here's your A and your X, A and your B, A and your B. What I always try to do with this is have when you add numbers together or try a function out, give yourself unique numbers. So when they add, it's something unique. If they subtract something unique, don't make one all 0s and all 1s, because then what if they were crisscrossing and adding? You wouldn't necessarily see it. So use different data. It's generally pretty safe with a lot of testing if you just go 5, 6, 7, 8, 10, 20, 30, 40. When they cross, multiply, subtract, or whatever, you can kind of detect which slot it landed. So packed just goes straight down. X gets processed Y and Z and W. And that's going to happen 1, 2, 3, and they all happen at once. So it's kind of like you set up all the rollers and the rollers just add them together at the same time. Single says, The registers still have 4 elements, but we're only gonna add the first one together, the single one. So all we're adding is the first X. And then whoever is the first guy, that's the one that gets copied over. So this is when you just want to add just the X component, but you have your data laid out in 3. Okay. So here's a reference to this stuff. The gold standard, this Microsoft stuff is pretty good, but it's kind of been deprecated in a way because people haven't been keeping that up. But the gold standard is this. This is intrinsic website by Intel. Intel actually makes sense that it's written and supported by Intel because Intel is writing the instructions. So they know how the instructions work and everything else. So you'll see for this class, because some people have old computers, some people have super new ones, some people have ones where you turn it on, it has so much power, it dims the lights and the airplanes change their course overhead. Other ones are like going, look, I can run for 15 days and I don't even lose power, right? We all have different variables. And so we're gonna stay, in our case, anywhere from MMX through SSE 4.1. Excuse me. And the reason for that is that's what's on everybody's machine. Now, some of you have this really insanely new instruction set. That'd be an awesome kind of noodle around project, because if you learn the extended set that we'll talk about in a second, you would probably be one of 5 people in the world who know it. And that alone probably can get you a job. All right.
So when you say that range, that's a range of sections in the manual?
Here, I'm sorry, here. So you click here, anything that's in those sections are cool for this class. Even if your computer can do with higher stuff, don't go higher, right? So what's nice here is you can select these, right? And you can say, I want arithmetic, here's all the ads. Then you're like going, okay, I only want, here's add. You start learning this add underscore PS, right? And so add parallel, right? And how this works is, here's the instruction. And this is now, this code, you can figure this out. It's not that hard. This is compiler speak, how they do the notation, right? And if you just stop for a second and just think about, I have 4 registers, how do I add them together, right? So here it's like add, right? So there's the add. And the first one goes, I'm going to go 0 to 3. So J is going to be 0 through 3. So there it is, J is getting updated there. So what you're doing is imagine J is 0. Then you're going to do all the bits on A, that's 0 to 31, plus all the bits of B, 0 to 31. Those will get added to the destination 0 to 31. So basically it's adding the X component. All right. Then you go J is 1. So now you go all the values from 32 to 63 of A and 32 bits to 63 of B going to the destination. So you're adding the Y component, then the Z and then the W. So you just take a step, but that's also why it's important to do an experiment. I'll show you how to do an experiment. Right. Next week, we'll talk about latency and throughput. Those are important as well. So when we go through this, the rules of our game is there's a puzzle and there's gobs of instructions you're going to use. And you'll see some instructions just are silly and there's no way you would ever use them. But you're going to do a lot of adds, multiplies, and subtracts, and stuff like that. But you can't go higher, right? Virtually nobody knows how to use the 512. This is a register that's 512 long, right? So 512 long, right? 128 is 4 floats.
Yeah.
Double that,
That's
256 is
What's the point
8
of that?
floors.
What is the?
So no, so 512 is 16 floats. Oh, that's the size of a 4x4 matrix. So you can do a 4x4 matrix times a vector. Thank you very much. I'll have a coffee, thank you.
That
Is silly sauce. So if you know how to, if your computer does this, and you noodle with this, you should be able to get a job in some kind of high-end optimization for trading or something like that. All right. All right, so this is how we'll use it. So now let's go a little deeper into this. So SSC2 came out. Trying to think. You guys want to do break? All right, let's do a break.
Body needs some rest.
What was the class you recommend for this? I think you said you-
Optimize C++ multi-threading. For use especially. See what the, I don't know what the number is. We changed the number, so that's like,
C++ multi.
it probably optimized multi-threading.
Does Google care about the order of
I don't
things?
know. Oh, there's 562. That's it. There you go. Yeah, it was called 400, and I'm like, going, why is this class of 400? This course is horrible.
Okay,
We,
this is in the fall, okay.
yeah, all we do, you'll like this. We'll have 3 lines of code on the screen, and we'll argue about it for 3 hours. It's like, we're in the low level optimization of the multi-threading
Okay.
library. So it's really cool. And there's 2 projects in there. One project we make, we have like 27 threads spinning around doing very fast pushing in synchronization between all the threads. The second one is, the maze when you see a little kid have those walls and you kind of draw your pencil around all the walls until you get to the exit.
Yeah, I used to draw those all the time.
Where you have, just walls all over the place. We do, I don't know, 20,000 by 20,000 grid. And I write it in C++,
Yeah,
the solution, and I optimize it.
to what, to generate,
So in
to
debug.
find the path or
yeah,
generate the
to-
maze?
No, to find path. It takes my thing in debug like 3.5 hours to do. In release, it takes like 3.5 minutes.
Yeah,
Then you can use this, more than 2 or 3 threads, as many as you want. And people are getting like, 30 seconds, 40 seconds. So it goes from 3 hours in debug to, 3 minutes in release, single threaded, then you add multiple threads in 30 seconds.
yeah.
So it's kind of cool. But it's like your mutex locks are really slow. So you're learning like why
Yeah,
and
the
when.
low
to-
latency stuff. is
And then you're like,
really locks.
then you think about like, oh, I'll use lock free.
Yeah.
Really? Lock free, maybe lock free doesn't mean it's fast.
So we, the low latency stuff, busy spins the cores, and uses lock free, and because it's almost like IO anyway. And I don't know, that's kind of like the level I haven't been at yet.
Yeah, and so you get to.
I mean, I
play
know
with-
what these guys are doing, but
You'll get in there and start arguing with them. So that'd be cool. I think you'll like it.
yeah.
But it's not a lot of code in class. Everybody's like, there's only 2 big projects. And then like a couple baby basics.
Yeah. Yeah, all right, so. This guy I would work with said, oh, yeah, okay. say that won't take the relationship based.
I'm so lost.
The spoiler you're talking about, is it literally just the actor being in the movie?
Yeah.
I thought it was a spoiler nowadays.
No shit, it does, because you know that fucking. Yes, that counts as a
That does
spoiler.
not count as a spoiler.
Because no one knew he was in it.
Actor
He wasn't in
plays
the
in
cast.
movie.
Because he wasn't in the casting list.
What?
Did you care if I spoil Multiverse of Madness?
Depends what the spoiler is.
It's a very minor.
There's
The
an actor.
characters,
There's
the
an actor
actor's
being in
only
the
in it
movie.
for like 5 minutes.
Oh, it's
Because
not a
someone's
real
told me
thing.
this just now. I'm like, you bitch.
I don't really.
John
care.
Krasinski.
I don't know.
Who? John Krasinski.
Oh, yeah. Who would he be playing as?
People have wanted him to do Mr. Fantastic. And they
Oh,
didn't.
yeah, that's
They
right. I
hated
saw
it.
that.
Like
remember?
Jim from The Office?
No.
Yeah.
Yo,
No.
He would look cool though, because he got the gray streaks and
Yeah.
yeah, it'd be dope.
But like, I'm like, why would you send me this?
That's
Because
actually
I'm
pretty
really
cool.
seeing
There's
it.
more
I'm
than
seeing
that.
it.
I saw something
Oh,
completely
yeah, I saw a lot more.
unrelated.
I'm like, why are you sending me this? I'm seeing it tomorrow. Like,
The trailer even says like, oh, it's something about the Illuminati, and I'm
oh,
like,
the
I know
trailer-
who's on the
yeah, everyone
Illuminati.
knows who's in the Illuminati.
Yeah.
So like at that point, I'm like, oh, he's gonna be in it.
Yeah.
He's on the Illuminati, but I didn't want to actually see it.
Yeah, so is Professor X. That's what I was like.
Oh yeah, that was already confirmed because they showed his yellow.
Yeah, his chair from like the nineties.
That's hilarious that they did
I was
that.
like, yo, that is dope.
What are you looking at?
I have a website that has pirated videos.
Piracy, my favorite.
There's no way you're gonna get it on there.
I
I don't
I
know.
don't know, man.
It's just
You can
today.
get every fucking movie possible on here.
Even the bad ones.
Even the bad ones.
Yeah, like Troll 2.
Especially the bad ones.
Troll 2.
Yeah, every single, what's his name? I was watching a video.
There's a movie called Cow.
Wait, is that the one with like the Kung Fu cow?
I don't know, it just says cow.
It's a
It
picture of a
literally
cow.
says cow. It's a picture of a cow.
It's probably a student film from like.
I don't know.
Have you seen Thanksgiving?
What
What about Velocipastor?
There's also a Santa Slay, Slay spelled S-L-A-Y.
Who would go through the effort of pirating a student film?
Fucking
Alright. Carol, you gotta watch Velocipastor.
I've seen like a snippet of it,
It's
but I need to
great.
see the whole thing.
You know what it is, right?
It's pretty
Especially the movie
fucking.
about Blockbuster as a pastor.
No, well, kind of. He's a pastor. He's a very devout pastor and goes to China, and this ancient man gets him like pastor, like powers to turn into a velociraptor, and he fights crime.
But when he turns into a velociraptor, it's that inflatable dinosaur costume.
Yep.
It's just,
Yeah, that's why it's great.
there's a scene where like his parents get blown up by a car, but instead of like you seeing it, it just literally is a blank screen. It says VFX sounds. Like VFX car explosion. That's all it says.
So it's like a joke movie.
Basically,
Oh,
yes.
100%, but it's
The
like,
budget was so low. for
it's
it.
good because of that, because they do it in the right way where it doesn't make it bad good, where it's actually like, wait, that's actually clever.
They're trying to be bad.
It's not
That's
like
what
Troll
makes
2.
it funny.
It's not like Troll 2.
Dude, it's fucking hilarious.
Yeah, I've seen clips of it. Oh, Shaolin Shocker. Another great one.
I'd probably spend more on the freaking, what is it called?
Nah, I can make that in like 3 hours. Graphics art, you get paid. No one graphics artists don't get paid shit.
They still probably paid more money for the part though.
Let me see that. Slight drop channel. Nah, you can make that in like a good VFX artist can make that in an hour. Most VFX artists go based on hour or commission.
Anyway.
It's not a watch.
But like, the guy that I need to talk to about that position is, you know, we're launching the EBS go live is May 16th. So it's like, yeah, I mean, well, we've been working on the, you know, we did Broker Tech first and we've been working on EBS since
That was 100% like a
2019.
So money for what?
This is great.
Cruisers is amazing.
It's shower cream and cheddar. Surprisingly good.
It just looks like original, like the bag makes it look like original.
Yeah, it does, but it's not. You have that
Where's the
little, that
time
little
place?
circle of sour cream.
Yeah.
Yeah. Oh yeah.
Well,
Here,
it was
here.
hard to see from here because it was out.
I'm gonna show you Shaolin's Shocker. Shaolin's Shocker. I can't speak today.
All right, just a reminder, class next week and the week after will be Zoom. I'll send more emails out, but I'll be up at the Mayo Clinic in Minnesota.
It's a bunch of ninjas that decide to play soccer.
All right, SSE2 came out and it added 32 more instructions. Well, it added some more instructions, and it was all sitting on top of the Pentium 4. So it added 70 instructions. Now you can use double precision, right? So now you can hold 2 floating point doubles in your 128-bit register, right? So it really feels and kind of behaves more like the MMX, but in double precision. So the extension is DP, and so that's really not that useful for a lot of fast development, but they do have it, right? So then SSE3 came out in 2004. They added 13 new instructions, and it's mostly integer extensions, right? So we're not that worried about that. Then SSE3 came out, supplemental streaming SIMD extensions 3. And they didn't want to rub it to number 4. So my theory is this, I've seen this happen once before. They release an Intel processor, and after they manufactured, they're like, oh shoot, there's a bug. So they said, okay, well, we'll just not, these functions just aren't allowed, and go with it. So that's what I think this is. This is the spin where they fix those bugs. So that's why it's supplemental to 3. This should have been in 3 anyway. So they added 16 more instructions, right?
SSSC.
All right, so SSE4 came out. And this is 2006. So then, it kind of settled out and came out in 2007, added 54 instructions, right? And then they finally got a brain here and they said, you know what, let's not keep adding supplemental things. So they go, was 4.1, 4.2, 4.3, they do it that way. So 4.1 has 47, 4.2 has 7 on top of that. And so 4.1 added instructions for HD TV. So the reason why you can watch high definition TV on your laptop or your computer is because of these instruction sets. So they realized, they said, what is the high definition TV using a lot of? What functionalities? They put it as a specialized instruction. They also added the dot product, right? In 4.2, they added the cyclic redundancy checksum 32. So that's used for the TCP header to make sure that your data is actually checksum and protected. And so it's nice that the checksum is actually a SIMD instruction. So here's where it gets weird, if that's not weird enough. SSE5, they started to change some stuff, started to grow this out. So they're like, oh, wait a minute, we want to beat AMD. So instead of just keep refining and reworking on the existing 128-bit, they spec'd out a 512-bit register. They can't make it yet, but they spec'd it out. So they started thinking in the future, like someday we will have 512 bits in one register. What can we do with that? So they added 512 bit and 512 registers, right? And they add multiply and accumulate and a couple other different things, right? So this class, we're going to stay in 4.1 or under. But what if you were writing this in the wild? In our class, where we have our computer, we're doing this stuff. What if you want to write compiled code and you might hand it to your customer, and your customer has a very cost-effective machine that doesn't support this? Like I call my mom's PC, where she got a PC for $150. It doesn't have these features. Or you want to write something to use this 512-bit register, and this other PC doesn't handle it. Well, you can determine this by using CPU ID and CPU ID extension flags, and this tells you what version you are. So what I've seen some people do in the wild is they would have a couple executables, and the first thing they would say, what version, what can your PC support? Okay, load up this DLL or this DLL. And they would just swap the DLLs based off of what it can support. For our particle system or particle contest, you cannot go past the 4.1. So if you use some option that's over 4.1, it won't compile on the testing machine. So so you get a 0 on it. So don't go past 4.1. All right, it's completely a puzzle, and you get access to really too many functions, and you don't know which functions to use. So what you have to start doing is start like dividing and conquering, experimenting, and put this stuff together. And if you do your code right, you'll actually speed up and beat your C++ version. Keep the manual open. Start with unique data. Multiply together, subtract, understand the function before you use it. Some of these functions do not work in the way you think they work. So you have to experiment with it. So here's an experimentation. I just use, create 3 vectors. First one's A, 1, 2, 3, 4. Second one's B, 10, 20, 30. And then if I just call add, I look at the C register and see what the data is. Because all those values are unique, I can detect what additions or how this function is really behaving, just to kind of reinforce it. Right, there's a transpose function. And how the transpose function is, whatever's a row becomes a column. Whatever's a row becomes a column, so we can transpose and kind of reweave this. This is a cool function, but it's actually slow. So the goal is to try to never use transpose. So transpose is slow, but a lot of people use it because they understand the math a little bit easier with the transpose. The catch there is reverse engineer it and see if you can get away from the transpose. Right? There's a dot product. Now, surprisingly, a dot product is generally useful, but I feel like this one's slow. So how dot product is you have a x, a y, a z, a w, and you have bx, by, bz, and bw, and these are multiplied together, and then the result is added. Right, so that's a dot product. With this function here, they allow you to kind of mix and match and do what you want. So let's say here, we wanted to do ax times bx plus aw times bw. Don't ask me why, let's pretend that's what we wanted, right? And where do we want to put the output? Well, we want to return it in location Z, right? So this will show you the flexibility, right? So let's say that's the weird equation we want to do. So do you want X versus X? Yes, so this is a 1, right? Do you want Y versus Y? No, that's a 0. Do you want Z? No, that's a 0. You want W? Yes, that's a 1. Then that's your multiplications, right? So only these two will get multiplied. Then you're adding these together, and then you want to be thrown into Z location. So you want this is a 1, and these are zeros. So now you look at your bit mask. Your bit mask is 0, so it's 0, 0, 1, 0. That's this. Then we go here for this bit mask. It's 1, 0, 0, 1. Right? So you would place in here 9, 4. Yes.
This is for cross product, because you can put in some negatives and do some nonsense.
There's no way you can do a cross product in 4 multiplies.
I guess it's 6.
Right? But yes, we're going to do cross products. Yes.
Yeah, I was just doing that. Yeah,
It is 6. I'm not crazy, right?
yeah, I think it's 6.
Because it's 2 subtract 2 subtract 2 subtract.
We'll go through it. Yeah, and this is the lane you talk.
How do you? Is there a way to like flip it negative? Like, yeah, I did this, but now put the negative answer.
There's instructions that will negate the result.
Isn't that also just, yeah,
Cute.
it's built in too for like,
There's a lot of things built in. There's a bazillion things. I'm saying this is just a dot product. The other weird function was the transpose. Right. Right. So starting in Visual Studio 8, and what's historic about Visual Studio 8, Herb Sutter became part of the team in Visual Studio 8. They called it 8 back then before they started doing, 15 and 19 and stuff like that. So he basically, without a mustache, added this function here, an advanced instruction set, and you could pull down and say, generate my SSE instructions. Again, we can't go past SSE2, we can't go into AVX, but the catch is as long as your code is aligned, you can flip this flag on and suddenly you get some performance. So the reason why I like this is you will see it's hard to write SIMD code. You will beat everybody's times, you'll get good times. but it's a lot of work. So what I always tell people to do is write your code, make sure they're using this alignment directive, and then go to the compiler, go, dook, turn it on. It gets you 80% there, and you spent the work by just turning on a flag.
Oh, so you just have to align it, right? No.
Right, as long as it's aligned, you create the environment, then this flag will work. If your stuff's misaligned, the flag, this is gonna do nothing. So this gets you 80% there. What we're gonna do is do the rest, make it 100% as fast as we can.
Will it generate code that's against the rules for the assignment though?
Oh, the assignment is, you have to do it by hand.
Yeah.
This is off. Yeah, if you change the flag, I'm gonna nail you.
So when you say like things are aligned, it means you're putting them inside those unions.
Yes.
Okay.
Yes. Yeah,
Just
and
to make
so,
sure like.
just as long as your vectors are aligned or your matrices are aligned, your data is aligned, then when you turn this flag on, the compiler goes, oh wow, now it goes faster.
We're not allowed to do that.
You're allowed
That's
to
the
do that in
part I'm saying.
particles.
Yeah.
You know, you're allowed to do that in your project settings for PA5. But you can't do that for this test. I want you to write the machine code or the SIMD code yourself. Yeah, right. And somebody goes, well, I'll just turn it on and look at what they did and copy it. And you're looking at assembly code. So you don't even know what the intrinsics are. So it's virtually useless. But this is really cool. So like right here, you'll see the flag. See, here's the choices. So we can't go past SSE2, but there's other ones in here. So, and those are free. You know, all you just flip on the flag, so you can get 80% there by just turning on a flag, which is kind of cool. All right, so now we kind of get into the fun part. So AVX is the next instruction set after SSE4. And it's advanced vector extensions. And so that's AVX. They have, then they further say it's AVX 256 or AVX 512, meaning it's 256-bit register or 512-bit register, right? Then there's the VEX extension to AVX, which is the vector extension on top of the AVX instruction set. So that kind of expands it more. Then you got the extended vector extension of AVX that uses SIMD, right? So this just becomes like crazy things. But the whole thing they started to do now is you can start doing multiply and add in one cycle. We call it max in signal processing, multiply and accumulate. It's a primitive kernel that you use in convolution. Convolution is used in all kind of things. And so it's really nice that in the year 2010, I mean 2020, they are up to what we had in 1980 in the old telecom days. So it's kind of interesting, a little slow. All right, so here's the layout. This is kind of crazy. So they wanted all the old functions to work in the new functions, right? So 0 to 128, 127. So this 128-bit, this registers are the SSE instructions, data set, right? Then when you go to 256, you know, so the first, so you have this, you have 15 registers of 120 bits. This is the SSE. Right, then if you take all of this and go double wide, this is AVX 256 or just AVX, right? And then if you take the whole wider thing, this is AVX 512. And what's nice about this model is that your code will map into these registers so it's backwards compatible. So even with the new processors, your old SIMD code will still run. So if you think about it, 512 gives you 16 floats. So across one of these things is 16 floats, right? And you now have 32 data lines of 16 floats.
Okay.
So you, it's pretty lethal what you can do with this.
What do you do with this?
Matrix multiplications, right? And you're getting this hardware assisted boost to this. So if you think about it, the reason why, what words I'm looking for? Like Python works, is useful at all is because it links to C++ libraries. And the C++ libraries are written in SIMD. So the whole reason why you can do all this
Like
data.
NumPy?
What?
You're talking about NumPy?
There's a ton of them that do it. So, but basically when you call a library in Python, more likely than not, it's because the math heavy library is written in C. I'm sorry, C++. And so this is where it gets the benefit. Oh, okay, so that was the last slide. All right, then we go into math. Hold on a second, I want to show you one more thing. There it is. All right. All right, so this guy here is he talks about the hardware. So this is how, you know, like if you're gonna learn systems, this is the better way to learn systems, but here's the slide I wanted to show you guys. So if you sit there say a matrix multiply, how many cycles to do in straight Python is 1, right? As soon as you do it in C, it's 47 times faster, right? Then if you start adding parallel loops in this, but when you get down to doing it all in SIMD, it's 63,000 times faster than straight Python. And this is why the SIMD stuff is, you know, gives you that heavy parallelization, but also this is why a lot of the Python libraries are written in C++. Right? So you got super slow code and then goes, boom, it gets onto this super fast highway and just does a math thing, goes back to the slow logic code script, and it goes back to this highway. So SIMD, you know, on that AVX 512 can get you 63,000 times faster, which is pretty amazing. All right. So and that launches in Bean because everybody needs to use Bean. This scares the crap out of me. All right. All right. So I'm going to go through vectors quick and dirty. We're going to be using vector multiplication. So what are what's what I'm saying? What you tend to do in SIMD is vector math. You do vector adds, subtracts, multiplies, matrix multiplications, vector multiplications. And so I want to give you a quick primer on this stuff. Don't worry if you do not understand a lick of this. The real caveat is everything I give you, I'm gonna give you the C code. So here it is in C, and you just got to make it work in SIMD. But you know, sometimes it's good to kind of see what is a vector, what is a matrix, right? So let's get in here. So matrices, right, are basically, it's a row of numbers and you have rows versus columns. So here's a row, row. So this is 3 rows and there's 2 columns, right? So the size or the dimensions is it's row by columns, right? Row by columns. So you can see this last one is 2 rows, 4 columns. There's a 3 by 2. In math land, everything starts with 1. So the first index in math is 1. In computer science, it's 0, right? So that'll play a factor in a little bit. All right, so if we're adding 2 matrices, you add like locations. So yeah, the upper corner to the upper corner, the bottom corner to the bottom corner, right? So here's the bottom corner, here's the upper corner. So you just add like locations. Same for 3 by 3 or 4 by 4. Subtract, you subtract like locations. So if you're going to subtract this one from this one, it's going to go into that location. Position, everything starts with 1. So 1, 1, row 1, column 1 is A. Row 2, column 1 is B. Row 1, column 3 is C, right? Row column. Transpose just means swap the rows for columns and columns for rows. So you go across, it goes down. So ABC becomes ABC down, right? The dimensionality is also changed. If this A is a 2 by 3, you swap it around. A transpose is a 3 by 2. And we denote transpose with a superscript T. So we just swap rows and columns. So when you see that transpose function in SIMD, it's going to take the row and it's going to become the column. The next row becomes the next column. And that transpose function in SIMD is very, very slow, right? Matrix multiplication. You're going to basically do a dot product or a special multiplication and add. And so let me just give you the pattern. You're going to go across and down. So you're going to do A1 times B1 plus A2 times B3. So cross then down, right? Now, you're going to cross in the first row, down in the first column, first row, first column. It's that location. Right? So just remember cross and down, cross and down. Again, if you don't remember this, it's okay. I'm going to do it all in C++. So you actually see me multiplying this. You're going to translate it to SIMD, but I wanted you to felt wrong if you didn't see some math. Right? So cross and down. I can't emphasize enough. Across and down. You just multiply 2 matrices, always across and down, across and down, across and down. So 3 by 3.
Sorry, across then down and that gets you the first position.
First one, and then okay, so then this is think about this. This is row 1.
Yeah.
Column 1, right? Then you go across and down. That's column 2. So row 1, column 2. That will be this location.
Okay.
Then you go row 2, column 1. That will be this location. And row 2, column 2. This will be this location. So this is just matrix multiplication. Like I said, I'm going to do it all in C++, so you'll see it in C++, but you know, if you're wondering what's going on, this is what's going on. Right? 3 by 3, same pattern, just more numbers, right? So boom, cross then down. So we do a cross. This is row and blue. This is row 1 and column 1. So it goes row, and this is, sorry, row 1, column 1, right? This is row 3, column 2. You start with
Yeah,
one.
it's column one, column two.
Yeah, it's horrible.
I don't know who created this idea. This is,
Yeah, it's only been convention for a couple hundred years.
yeah.
But so row 3, column 2, you'd be in row 3, column 2 is where your answer goes.
We need to do this without for loops,
You can do for loops, you just won't get a good grade.
because it'll go slow.
Loops are just will bring it to your knees.
Right.
Because what does a loop do? Right? Let's see. So I got a white sheet there. All right. So for right. It's going to first line here, test the condition. Right? Does your body, then it's going to do the second line, increment it. Then it's do a go to here and call the condition again. So you have a go to, a jump, you have a conditional, and you have some kind of generally an increment or some kind of movement, right? Or I can do my array and just write down A0, A1, A2, and just do it all by hand, no looping, and that will go net faster.
It's just more typing.
A lot more typing.
Oh, man, that's so worth it. You're running on the whole array.
Now, compilers are generally smart enough to see, oh, this is a for loop, and they try to optimize it. But when you're writing assembly code, optimized code, you're not writing for loops if you can get away with it, especially for SIMD. Because by adding a loop, you probably lost all the benefit of SIMD just because you decided to go by for loop, right? So I need to maybe change the way this makes things work.
So on the assignment, like if things are not appropriately dimensioned, are we supposed to
They're
reject
all going to be perfectly dimensioned.
it? Okay, so we don't need to handle those if else cases.
No. Everything you're gonna get is gonna work. All right. So here's a matrix. And it has a dimension, say 3 by 4. And I want to multiply it by another matrix, n. Right? This dimension here. The inside dimensions have to match. So if they're the inside here, so 3 by 4, so 4 has to match the first dimension of n. And what you get as a result, is the outside dimensions. It's bad color choice. Right, so you're going to get here. And that's the only rule for my matrix multiplications is inside dimensions have to match, right? Now, historically, we do 4 by 4 times 4 by 4s. So kind of a mute issue, but there's other properties, right? And this is not going to come up at all, but A matrix times B matrix is not equal to B times A. You can't swap the ordering. So whatever you do to the right side, you have to do to the left side. Right, so this is not equal. So the only, so matrices have to stay the same. Right, if you had some matrix here, C equals, B, and you want to multiply by A, you put A on this side, then you have to put A on this side. Or if you had C and B, and you want to go, I want to multiply by A on this side, then A has to be on that side of it. Left, left, right, right. So to kind of go back to your old algebra days, remember when you did 5x equals 7? And it goes, hey, the answer is, right? And it'll go, oh, this is easy. You just go 1 divided by 5, 1 divided by 5. Oops, you're on the wrong side. We get away with that because a constant that has no sideness to it. We can actually multiply in any order. But what you really should be training from even when you're a little kid doing this is it should be on that side. Stay left, left, right, right. Right. So when we do that 5x equals 7, what we're really doing is multiplying by the inverse of 5. So here we have the inverse of 5 is 1 over 5. I wanted this to be red. This is the inverse of 5. So 5 times 1 over 5 equals 1. Right? And this is why you can't have an inverse of 0, because if you divide by 0, it explodes. Yeah.
Are we gonna have to do inverse matrices?
No, not
I think
in my other classes you do.
because that's floats and these are insides.
Inverses doesn't care if it's float or.
No, but I mean, you're not guaranteed to get ins on the way out. You can have an int matrix to begin with and end up with floats in the final answer. For inverses.
Well, they're all going to be the same type, right? So you're not going to sit there and say take an integer. There's really no such thing as an integer matrix, right?
Oh, okay.
You almost never use that in reality. It might be integer as feedback, but it would be more likely floats. So you always start off with floats.
Okay.
All right, so matrix land, right? Matrix. What is the 1? What is the number 1? You know, like when we go 1 over 5 times 5, we get 1. What is the 1 in matrix land? It's the identity. So it says zeros everywhere, and then on the diagonal, it's a 1. So this is called the identity, right? So if we wanted to do matrix times matrix inverse, we get identity. Or we go matrix times matrix inverse, we get identity. Because if you think about this just as 1, identity times any matrix will equal itself, because identity times 1 does nothing. Or you can do A times identity equals A, right? So identity is the same as 1 in matrix land, and inverse, you just multiply by its inverse. Okay, right? So now you get things like this. A matrix times B matrix times C matrix times D matrix equals E. And I say solve for C. C equals what? Right? So I know there's one guy's chomping at the bit, so walk me through it.
You left multiply by A inverse.
What?
You left multiply by A inverse on both sides.
So A inverse.
So you got an identity element on the right. So you got
Right, so
BCD.
then this becomes identity. And then identity times any of that, it just falls out, so you're really left with this.
Yep. You want me to keep going?
Mhm.
And
So
you-
then you get rid of the B,
the
B
inverse.
inverse, right? And now you're left with CD equals B minus 1, A, E, right? Then you're like, okay, I have to get rid of the D inverse. Now D inverse on this side. Now, there you go. Right? We're not doing that math, but just wanted you to just kind of see it. It's not hard, but so the reason I bring this up is we're getting into this matrix stuff, right? So we can multiply any matrix times any other matrix as long as the dimensions, as long as the insides are the same, we get the outside. Right? All right, a matrix is a set of numbers. It can have any dimensionality, but if one of those dimensions is 1, it's a vector. So we can have, X, Y, Z, and here's our matrix. What is the dimension of this? This is a 1 row by 3. So this is a, right? Or we can have a vector that looks this way. X, Y, Z. This is a 3 by 1. If there is the number 1 here, it's a vector, right? If you have just one element, 1 by 1, this is a scalar, right? So scalar vectors. We can talk about this all day, but I know you guys don't want to. So what you really think about at the end of the day, everything's matrices. It's just, sometimes they're scalars, they're only one dimensional. Sometimes they're vectors, or they're n by n, right? All right, so because of this, we can just sit there and say, you know what? Here's a vector. X, Y, Z, W. Here's the matrix. M0, M1, M2, M3, M4, M5, M6, M7, M8, M9. Right? So we look at the dimensions here. This matrix is a 4 by 4. What is this vector? A 1 by 4. We're allowed to multiply these together because the inside dimensions are the same. Right? This vector is a row, so we call these row vectors. Right? And how do we multiply it? Across, down, cross down, cross down, cross down. If we have a matrix, right? So this is a 4 by 4. What we want to multiply it by something here, we know the next term has to be a 4 because these two have to be the same, right? So we do 4 by 1. This is a vector, and this is a column vector. Right? How do we multiply this? Across and down, across and down, across and down. So whether the vector is this direction or that direction, as long as the dimensions work, it's the same multiply, right? People will confuse the shit out of you saying it's row major, it's column major, we pre-concatenate, we post-concatenate, blah, to all that. It's just multiplication, right? So just worry about the multiplication. So here's a vector times a matrix, 1 by n, n by m. So we're allowed to do that, right? So vector times matrix, across and down, first element, across, down, second element, across, down, third element. So when we do a vector times a matrix, it's just really matrix times matrix. It's very specialized. And once you kind of like accept that, life goes a lot easier. Like going, vectors or matrices are all the same, they're all matrices. Just one dimension happens to be 1. Matrix times vector. As long as the two inside terms are the same, we can multiply. So across, down. You know, that give you that one. And across, down, gives you this one. And across, down, gives you that one. So same thing, and here's the answers there. And also I'm gonna have them in pseudo plus, so I want to kind of scare you. You'll see this whole thing about row versus column. And people say row, are you doing row major or column major? And this is a religious war. And I'll give you the origin of this and then the side effects here. If you're going to say it in English, and I say, I want you to multiply 3 matrices together. Matrix A times matrix B times matrix C. I want you to multiply these together, right? So what you would say, I say, write down the matrix. You go, matrix equals A times B times C. That's rho. And we use this in engineering. So this is for engineering. We use it for hardware graphics. Everything is. If you talk to a math guy, like, oh, I have multiple degrees in mathematics, they go, no, no, no. You have to multiply A and then pre-concatenate B and pre-concatenate C, right? Now, reality is you have to know if your system is row major book. It defines matrices as rows, or it defines your major matrices as columns. Now, I'm not going to get into this, but these two give you the same matrix. It's just one is the transpose of the other. These are all transposes of those. And when you do the transpose and you multiply together, you get the same answer.
Yeah.
So if you transpose everything and reverse the multiplication order, you get the original one in transpose order. So the catch here is if you see this, we don't care, right? We don't care if it's row major or column major, because from our perspective, we're writing fast code. We just say, here's two matrices, multiply them together. And when we multiply them together, it's the same way. Nothing's changed. So don't get kind of snookered by the concept like, is this row major or column major? We just always multiply the same way, right? So graphics cards, everything is row major. Mathematics pure people are going to use column major. But when you read a book, and if it's written by a mathematician and it's for a math audience, you got to know that. If you're reading a book that's like 3D graphics in DirectX, you're like, oh, that's row major. But a matrix times a matrix is still the same matrix. Nothing's changed, right? So I know I'm kind of going past this a little bit here, but to make the dimensions work, we do 4 dimensions. So we're just going to add 4th dimension generally at the last location. We don't care, we're just going to use it. But dimensionally, it still works. All right, so yeah, and then I add some stuff here just for graphics, so we don't care about this. Boom, boom, boom. Right. I think the rest of this is kind of useless. Okay, here we go. So a matrix times a scalar, we just multiply the scalar through it all. A matrix times a matrix, 4 dimensions. Right. But it's just as simple here, across and down. Nothing's changed, right? So that's it on the matrix. So let's see what we're going to do with this class, this material. Cool, got it. Just the right amount of time. All right, so you have basic 6, I think, and PA6 already in your inbox. So you can start on this. Let's talk about basic 6 because it's a 2-second deal. STL, right? Ooh. So STL is something that every time I use it, I look it up. STL is really large, and basically, from a teaching perspective, STL is horrible because it does linked lists for you. It does trees for you. It does auto growable arrays for you, right? It searches for things, it sorts things, it finds things like, oh my God, this thing's fantastic. It's actually quite slow. And a lot of companies use it. And I think it's because the programmers don't feel comfortable writing their own. Right? So they're like, oh, I can screw up the linked list. Now, everybody's kind of smiling now because you made it through the memory system. We're like, oh, I know linked list. At least one thing I know out of this class, I know linked list, right? But think about how you were on that first week when I gave you a linked list problem, right? Most people graduate not taking my class, and they're like, linked list scares them. So then when they get into industry, they use containers. So they use a list container from STL or a list container from Java because they don't trust their own ability. What I want you to realize that you have the ability to write it, and you can write it faster. You can customize it. So do it. But there's a lot of legacy code out there. And also if you're writing tools, right? God invented cloud and server farms, because you can throw code and say, cook overnight, cook for 3 days, cook on 20 machines. And if it's 4 times slower, it comes out, right? So on tools and conversion, a lot of times we'll just like just make sure it's correct and out the door. Just for kind of life survival skills, right? So this one's really simple. Here we go. So here's an STL. So the first problem here, there's only 4 problems. Here's your data. And you're going to put it in an STL vector. STL vector is an auto-growable array. So it's an array you can add to it, it automatically grows, it can search and do all these different things, right? So initialize this data. So initialize this somehow. Whatever it takes to initialize, replace this line, initialize a vector. Then this next line here, I just copy a vector into my unit test so I can test it. So this is the code. You have to replace this line of code here and replace it, initialize a vector. So at some point you're going to have, a vector equals blah, however you set it. And then what I'm going to do in the unit test, I'm just going to check it, say, okay, is the array correct? Is the original one? Is, everything is kind of matching. So that's all I do.
So we're still using STL, but
Yeah.
there's something wrong at the STL that we have to fix.
No,
Just load that data from the test.
The problem I have is, how do I test STL?
Oh,
I need a copy of it.
Right.
So what I'm doing here is you initialize it,
And just copy.
and then I copy it, and then I check it.
right.
Then here, you're gonna imagine there's a million numbers in this array, right? And between the number 2 and 8, you're gonna insert the number 5, right? What I don't want you to do is do a for loop and do all this other stuff. There's special commands in STL to do this faster. So search for it, learn how it is, and insert it. And the next one is you're gonna sort this array. You're gonna sort it from smallest to largest. So guess what? STL has a sort function. It's called .sort, and you give it a function and it does it.
Oh, nice.
All right, so this is pretty easy. So the next one here, you can do the same thing. So here's your integer, but now you're going to insert it into a STL list, which is a double linked list container. So how do you initialize it? Who knows? Initialize it. Between the number 22 and 88, you're going to insert 55. Assume there's a bazillion numbers. There's a way to do it easily. Then I want you to sort this largest to smallest. Right. Number 3 is we have this complex data structure, zip code, that has a name. Zip code, it's over here. Zip code, here we go. It has the zip in the an integer and then 4 characters, right? And what you're going to do is sort this smallest to largest, based off of the sort zippy from smallest to largest, and compare the function with the second letter of the string. The reason why I did that is to force you to write a comparison function that you add to this function. Otherwise, you can just call sort. And it's like, oh, it's strings. It probably will do the right thing. So force you to do a little different. This one here then is I want you to find the iterator to find this node B and then this data set, and that's in here. So here it is. And you're going to search through that list. I'm sorry, this is a set. This is an STL set. STL set is a balanced binary tree. So you don't have to worry about the tree. You have to worry about how to call the functions to load it in the tree and how to call functions to search for the tree. Which you just call dots, find and stuff like that. It's not that hard. That's why people like it, because it makes you look like a star, right? Then I want you to find the name associated with this data. And you have to, you probably should use a custom predicate. If you know what a predicate is, that's the reason why you're looking it up. Right? And this last one here is, here's a vector of 3 data elements. You're going to insert this into a vector, right? And then what you're going to do is you're going to sort this in strict weak ordering. So does everybody know what strict weak ordering is?
Talked about it when we did.
Yeah,
strings.
didn't you do this like a few weeks ago?
Okay, cool. Then we're on page. That's it. So this is really easy basics. All right, so in the PA6, you're going to do several source code here. So let's get the thing out here. You're going to write the SIMD stuff for these functions here. This triangle one here, right? This triangle is one interesting. This triangle function here is, so you'll see it says vector triangle, then it has an underscore SIMD. I'm sorry about the horrible long names, but this is when it says SIMD, it has the SIMD right there, right? And the do not modify, it will have the vector over here, triangle functions. And here's all the functions here, and then here's all the C code. So here's all the answers. You want to do a vector times a matrix, there's the answer. You want to do the length of a vector, there's the answer. You want to do a cross product, there's the answer. So everything here has the answer. Matrix, and then do not modify. Here's vector times matrix, matrix times matrix. A matrix is a union of 4 vectors. Each vector is 4 floats, or it's a union with 16 floats directly. Here's matrix times vector. Here's matrix times matrix. And then on the vector, we have a vector times matrix. So all the answers are right here in C++ and then do not modify. Your job is to now implement the SIMD version of this. So let's take one here. Vector times matrix. Vector times matrix. Here's your vector. Right, and here's your matrix. So now you're gonna do vector times matrix. So vector times matrix. You're gonna replace this function with SIMD. You got everything in your hand. It says replace that function, right? So then you have matrix right here.
So whether the vector is a row or a column, we should be able to infer from the dimension that matches up with the matrix.
This is vector times matrix. Remember the data, all right, so here's the secret. We don't care if it's row or column, it's just 4 floats.
Yeah.
So it's gonna be vector times matrix. The only way that could work is if it's a row major.
Yeah.
Right? Then, but remember, across and down, cross and down. Who cares if it's row or column? Then if we do matrix times vector, right? Matrix times vector, we have right
That
here.
can change either.
This right here, matrix times vector returns a vector. And if the vector is still 4 floats, and now you're gonna just be replacing this function,
Oh, but now it's a 1/4.
right? So now you're like on, ooh, matrix times vector, I get confused. It's fine. Go up here to the do not modify. So if you go matrix times vector, right? Everybody knows how to read this, right? This is we're in the matrix class. So this is a matrix is the first thing, and it takes input as vector. So it's matrix times vector. You just go up to the do not modify, and you go matrix times vector. There's the answer. You just have to make the SIMD.
Oh, so this.
I give you the answers. I just give them in C++.
So it can, so what happens in the test essentially is that it runs the operator
Okay.
overload.
It's gonna, yeah, I'm running both. So that one's the matrix times vector, right?
Right.
Matrix times vector. So performance test right here, matrix times vector. Matrix times vector. Here's three vectors, right? I create a matrix. I multiply it against, 3 different times. I check the values to make sure they're all happy. Okay, so I just prove it out. On the performance test, matrix times vector. Matrix times vector. I'm going to sit there and do the performance test, start, stop, do that test. This test is going to do this multiplication a zillion times. And then I can just time it. And then I'm going to now do it again in SIMD. Same data, same everything, it just has word SIMD next to it. Do this a bazillion times, measure it, and then do the division.
So we need to go to the Intel site and browse the link and find the.
Yeah, we're
right-
gonna start doing coding together
Oh,
to kind of show you how to do it. So here's the results. Oops, maybe. There you go. All right, so this is the results in release. So here's matrix, which is matrix times matrix, right? And we're roughly 2 times faster using SIMD. Vector times matrix, 1.5 times faster. Matrix times vector, 1.5. These 2 numbers should be about the same cost. Because it's the same number of multiplies, the same number of adds.
Effectively the same thing, yeah.
Okay, so lerp, we'll talk about lerp and triangle. Then we have these 2 things, row major and column major, right? And so row major, the time is 2.2 seconds. Column major is 2.2 seconds. Right? Do not look at the ratio. Right, and I'll explain why you get separate answers there. All right, so what is this doing? The row major? It's multiplying this vector times a matrix times matrix times matrix times matrix times matrix times matrix.
Oh.
Right, and then in column, matrix, 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 vector. So let's give you the idea of how to understand this, the cost of this. So a vector, x, y, z, w times a matrix, m0, m1, m2, m3, m4, m5. Okay, so we're going to do across, down, that's 1 dot product. Right, across, down, that's another one. Across, down, that's another one. And across and down, that's another one. Right, so what we have is this is 4 dot products. So the cost of a vector times a matrix is 4 dots, right? We're going to use a dot as like kind of unit of time or complexity or computation. If we have a matrix, right? Now we go across, down, that's 1. Across, down, that's 2. Across, down, is 3. Across, down there. This is 4 dots. Right? So a vector times matrix or matrix and vector are both 4 dots. And we saw a vector times matrix is 2 seconds. A matrix times vector is 2 seconds. They should be the same because the same number multiplies like in adds. Right? A matrix times matrix. Across, down, 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 there's 4. Across, down, 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 4. So it's 16. Right. All right, so now take our little legend here. Vector times a matrix is 4 dots. Matrix times a vector is 4 dots. Matrix times a matrix is 16 dots. Okay. So we're going to do the first one, vector times matrix times matrix times matrix. Now, obviously in our code there we have more matrices, but I'm just going to stop there, right? So what's these two are going to multiply together. We're going to get a vector out. These are going to multiply together, get a vector out. And then these multiply together and we get a vector, right? So we count this is 4, 4, 4. So this is 12 dots. Okay. Everybody follow me so far? Now we're going to reverse this. Right? All right, so multiply these together, you get a matrix. Multiply these together, you get a matrix. Multiply these together, get a vector. Okay, so this is 16, 16, 4. Right, so this is now 36 dots. Right. So we have a really interesting problem here. Vector times matrix times matrix times matrix is 12 dots. And then matrix times matrix times matrix times vector is 36 dots. Right?
These are with matrices that are 4x4, right?
These are for 4x4s. Right. So we look at our data. And the row major is 4 seconds in C++, right? And our column is 10 seconds. Well, that's 2 point something difference, right? We were predicting roughly a 3 times difference. Right, so what is 10 divided by 4? 10.2.
2.25 something.
2 and a quarter.
2 and a quarter about.
Yeah, so we got 2 and a quarter. We predicted 3. Our results was 2 and a quarter, but it's also optimized. But at least we knew it was going to be slower, right? So the question here is, how did I get this to be 2 seconds? Because I said don't look at the ratio. And my answer is 2 seconds, 2.2 and 2.2.
SIMD somehow knows how to.
No. Doesn't do anything like that. Now, we're going to do the matrix and vector backwards.
That's it. Yeah, that makes sense.
Matrix times matrix times matrix times vector. We're going to do it backwards. These two give you a vector.
Vector.
And these two give you a vector.
Vector.
And this gives you a vector.
Wow.
4, 4, 4 full dots,
So you just, yeah, it's really just reversing
reversing the multiplication order,
oh,
right? Huge difference,
yeah.
right? How do you do that? Okay,
Put
you
it
guys are gonna
into
love
the
this one, right? You're gonna like this one. So if I take my matrix here, let me just give it like letters so we can talk about it. If I give you a function that takes in matrix A, matrix B, matrix C, and vector, could you multiply this together reverse order?
Yeah.
Yes, you would just say V temp equals matrix C times V. Then you go matrix B times V temp, matrix A times V temp. Right?
Yeah,
Just
so
do it
you're just
backwards.
passing them into a function. That
Right?
is, yeah.
So how do you get this?
You create the function.
No, it's, you can't
Oh, yeah, Cindy, yeah.
proxies.
Ah.
So you basically push this all together in a proxy. Remember, proxy is Einstein and Bohr's favorite, C++ function, but it has no optimization value. All it does is says, here's a string of operators. And we just collect all the variables and say, here you go, and you do something with it. And the hope is that you do something smart and clever. So next week, we'll talk a little bit more about this part, but that's the whole trick, is that you're going to do your matrix multiplications into a proxy, then your proxy goes faster because you can change the order.
Right.
So what we're doing is we're taking, even though these are binary functions, this two will return a M to M, and then M to M cross with M gives you an M3M, then M3M crossed with vector, puts you into that function. And now you have all 5 variables or 6 variables in your hand, you can multiply in any order you want.
But you still need it, so you need 5 proxies or what? For this one,
Yes,
you need
you
3.
do need, this one, yeah, this one is 3, but in reality, you
You
probably
would
need
need
5.
to
And
accommodate.
you only need that function for the one with the vector in it.
That's it, yeah.
Yeah, so you can just have like dummy, well, not dummy proxies, but like something with
Just chain it together.
yeah, chain together.
Right? So that's why this is the same speed, because I'm doing the same number of dots. But in C++ land, it doesn't know about the proxy. So the original code just does it straight up. But we're gonna use proxy to reverse the order of multiplication.
If you were to not just use proxies for the column major for C++ directly, would it still only be 10 seconds, even though
If you don't use,
if you did use proxies for the original and the C because you just said
Oh, no,
that's 10 seconds without proxies.
oh no, we can look at the debug. No, I'm not using, I'm using proxies not only on the SIMD version. Because the other version is C++
All right.
raw, because we're seeing how, this is the code the coder made, we're gonna optimize it.
Right, okay.
So we want to leave that code alone. So that programmer probably does not know how to use proxies. It definitely doesn't know how to use SIMD.
So if you were to use proxies technically for but it would be like 4,
Proxies-
3, 5
Oh,
seconds.
it would
maybe?
probably be faster,
It's definitely okay.
because you can, if you use proxies and reverse the multiplication ordering.
Oh, you're gonna get really fast.
You have, that's what we're doing.
But it's just SIMD.
We're swapping the order of multiplication and SIMD.
Yeah.
If we didn't swap the order, that's this one.
4, yeah.
So it's 2 times faster.
Oh,
So just going from C plus to SIMD is 2 times faster. Right? But here, if we don't, we're 4.5 times faster. That's because the multiplications is working against us. The left to right is working against us. So that's kind of the thing. I included in Piazza. So way back, do you remember when COVID started?
yeah.
We had,
Oh, that video, yeah.
I I didn't even have a tablet, so I
Okay,
I
I'm gonna
took
do on this
my
last
marker
bit here
board
is actually do.
and just put a camera on my phone. My phone's upside down. It's recording it. And so literally it's just overhead. So this is me doing this. And so I'm going to talk about the vector. So if you wanted the triangle function, I take you from scratch. I walk you through the code. We actually type the code together and write the SIMD code together. So this is a full tutorial for that. So if you want to get through that one unit test, there it is.
There's the answer.
Yeah, but this way you can understand what I'm doing.
So
And
this
the link to the
also
videos
helps.
on Piazza?
It's on Piazza right now.
So this also helps just understand the SIMD, like
Exactly.
syntax and everything.
Right.
Okay.
All right, so let's code some together and so we can show you how to use this, but I can't emphasize enough. This primer video not only gets you one unit test done, but you also see kind of how to do it. So. Also, I think it's cool that I went retro with a marker, with a physical marker board, and nobody would have came up with that idea. Some ways I like it better because I can.
This is peak software engineering.
Yeah, it's just our old school, right?
That was in the spring when COVID first hit.
This February 2021.
Oh, this is even late.
Yeah.
This is
No,
a year
no,
later.
no, that's when I posted it.
Oh.
I posted it differently back then. This is much older video. Because I had it locally on my machine.
It's 5/4/2020 according to the video.
Yeah, then that was it.
Yeah.
How do you figure that out?
Because in the bottom right of your desk, like your hotbar desk,
Oh,
I can read that somehow.
you're got good eyes, man.
I can read too.
Yeah, so yeah, that's the spring of COVID, right? All right.
I can even read the YouTube.
So, all right, let's code this together. Let's start coding some stuff here. This SIMD is a rough, long one. So get through it, get really good, and then we'll spend a lot of next week's class also on it. This is a rough one. I don't know why I'm in this section. All right, so let's start with SIMD. So what I'm gonna do is I'm gonna start with the sandbox. And
Oh, I know.
always sandbox, and when you start to embrace the wisdom of the sandbox, you'll like, oh my God, this is so much easier. All right, so let's just do this. Create vector. All right. There you go. Here's vector, and then all right, so there's vector SIMD, and then well, let's go for broke. Boom, boom, boom. That's cool, that's cool. And then boy, you don't realize how you're used to your own keyboard. All right.
You really don't.
Yeah. All right. And then what do we have here? We have this guy defined. then we want to print function. Hate that. I had to figure out how to shut that double quote automatic gizmo off. So bites me. All right. P name. Plug and pray.
You're missing that.
Oh, yes, we
Yeah.
have.
All right, so let's just test drive this vector A 1, 2, 3, 4. A dot print. And then there's also, I think, some is it? There you go.
Oh,
GG will be reduced or show you decimal, it will figure it out.
so G just like base numbers, nothing else.
So here, like. Right. Kind of smart. All right. All right, so here we go. So let's do add operation. So vector operator plus const vector reference. Yeah. Right. And this is a const method, right? We're always throw const wherever we can. All right. And then boom. Here. C C dot x equals this arrow x plus r x. C dot Sorry, it's nothing more annoying than watch somebody type. I wish there was in the old days I used a different editor called Brief. And I wrote a macro to automatically increment all this shit. So you hover over the first one, it goes bloop.
Now, couldn't you just do all this in one return statement?
Okay, yeah, but let's just leave this right now, because it's readable. We're just doing this. So now here, vector B. Yeah, I don't know how many years it took me for like, I could put a string in there and give it a name. And it's like, oh, that's a lot easier. C. Print. C equals. There you go. Okay, so that's working. Okay. All right, so now let's SIMD it. All right, so go to Intel. SIMD. All right, add PS. Okay, there it is.
And PS is parallel.
Packed,
right?
yeah, packed, right? So underscore M PS.
That's just the.
And it takes in this arrow underscore M. R underscore M. This is going to return C.
What? Wait, so what's underscore? Is that, oh,
This
that's
is the variable.
That's
Yeah,
just
it's a variable underscore M.
Oh, so it has the struct part of it.
Yeah, so I can just do this.
Yeah.
Now, the reason why our code worked before, is because now this goes to the X component. So the union was working all along.
Oh, right, because M has like
It's
dot
just
X
everything,
dot
it's
one.
everything. Yeah.
Right, so now,
Oh, that's simple, okay.
all right, so what do we want to do here? You know, if you want to sit there and say C equals C minus D, and we'll do vector B is 100. And so let's overload negative and subtract that.
So just as simple as just changing that to like sub.
Yeah. So yeah, actually I'm doing like simple, easy ones here. So what did I do here? Oh yeah, it's C. So let's print out the C as it transforms. All right, so let's start doing some a little more crazier.
Ooh, proxies.
You know,
Oh,
so here's the C, and then we minus 100 from that, right?
Right.
All right, so the one that everybody gets screwed up with is add, horizontal add.
ooh,
Right? So let's just do. Okay, what if we wanted to horizontally add all the A's together? Horizontal meaning add the 1 to the 2 to the 3 to the 4. horizontally across.
Is there a function that just does that in SIMD that just like, just like sums the whole thing?
Right, so because we have all of our toys now, right? Now we're kind of dangerous, right? We can do this. A dot underscore M, right, equals. So let's do this, watch. You'll see, I'm a big believer in print. A lot of people aren't, but I'm like, going, you're missing the tree, right? So here we go, right? Here's vector C. Right, and we'll just do C dot print. Right. C dot underscore M. Underscore M. And add PS A. Boom. So we can play right into this playground here and start exploring. Right, so because I have the print function, I can just try all kind of functions here and see instantly my output. So, I mean, that's kind of cool and clever, right? So now let's look at the horizontal add. Here it is. Oh, what? So we'll do the first add, right? A and B, right? And what it says is in the first location, the X gets added to the Y and goes into the X. And the Y, Z and the W get added together, it goes in the Y. What kind of sorcery is this, right? So let's do this. Let's make C this all zeros. Horizontal add. All right, so what this is going to do, it's going to add these two together and put it into the X location. Let's put these two together into the Y location, right? So it should be 3 and 7, 0, 0.
Oh, that's
Pretty fucked up.
what's the point of that though?
No. No. Right? No, wait a minute. You're like, oh, Ed, this is silly, right? No, now we do this.
Oh, oh no,
Stupid 10.
no. You turn it to B. That's but the two and the, oh, the
It's
two
a
and three
third.
don't even matter. Yeah, it's just three.
Right? So in this case here, this is going, it goes in the first location. So this is where I do this nomenclature. I just do bracket, oops, and I'll say AX plus AY is in the first location. Then I go Z plus AW in that location. And then this should be BX plus BY, then plus B. No, it's gonna get better. Wait till you see this next move.
Oh, because it can be something.
BW, right? Right, so this is what this is doing. Right, you're like, okay, this is pretty effed up, right?
Yeah.
So right now, we did this all with zeros on B. But what if I wanted to add A horizontally, and I want to add B horizontally, and I want to do them together?
You just put stuff in the B.
So now,
So you're just adding the total values of each, basically.
right, so now we watch this. I'm just gonna break my hair.
I'm a genius.
So this is 3, 7, 30, right?
Yeah.
Yeah.
And now we do this again,
B 10, 100.
and the first two, right? Because We're not worried about the second one. So here's your answer. X and Y. So now, think about it for a second. I just added up 8 numbers in 2 instructions.
Huh,
Huh?
that's 4 times the.
Right. Right, but now let's say, but your goal was you really wanted to add all these together.
I know. Oh, just do another one while you have.
Right, and then where do you start to see, right? And then you're starting to understand the staggering.
We'll have to add all 12.
Right? So if you do this, right, where do you start C,
You'd have to start it.
right?
But-
Well, here, wait a minute, we'll call this D, just because I don't want to retype this. Where do we start D?
After.
After
second
CB.
That's useless data right here,
Oh, you started there.
right?
one. Oh.
Right? And that should be 300.
Cause then you'll get, oh, because C is not defined.
Oh, I screwed up C. So boom. So here's the beginning of it. And C, and then if I want to, so there's just one more cycle and I got C done.
Well, wouldn't D, oh no, D is not quite done yet, but you can finish D with a
No, I
single.
meant
add.
one more cycle D would be done.
Yeah, but you could still technically, if you didn't want to go an extra cycle, I mean, I guess what's the point not to?
No, you haven't finished your adding.
Right, but you would then have to get rid of the 10 and 100 there technically, right?
No,
Because that would get
at
overruled.
this point here, at this line right here. At this point here, your stuff, let me go back to this. All right, so here, this is C, this is A is in X. You know, B is in Y.
Right. Oh, so when you just do the C times D again,
Right, so this is your X, so you can grab it, this is your Y.
And then D is just those two.
and then,
Then you need one more cycle to get D,
right, and you just,
and that will land in X.
right, okay.
Mine X.
Right,
Well, because it would put them in X and
Right
Y,
here.
or X, yeah. That's why you need to extract what's there. And C, you just do C and D
and
again?
this could be anything, we don't care about the
Yeah, you
trailing
don't
rate.
care.
And this would be D, it's gonna land in X, and we don't care about the rest, don't care, don't care, don't care. Right.
Can you go back to the Intel page? I'm not sure I follow how to read that,
Okay.
the documentation on those.
But you see,
Oh, yeah, it's, okay.
so this is what D, how do we get 110?
Yeah,
Oh, here's
because
the
you have to
1,000.
do it
Okay, you're
again.
doing
wouldn't
C.
you?
Right,
It's in
Yeah,
B.
because
it's in C.
AP is the next right now, and B
Yeah.
is in Y.
You're adding A and B now, so.
Yeah, that's what I was confused about.
So it's in Y.
no, you're right, so I screwed up here, this should be,
That's right, it's just that,
Well, CD is right, because but CD's second is.
yeah, it's gonna throw this into the Y
Y,
location.
yeah.
So my comment field is wrong. Should be like this. Here,
you would have to do it again to actually get the.
No, you have D already. You know D's and Y.
Oh,
so it's right there,
Yeah, you know D's and Y.
because it's in the second location.
Yeah.
yeah.
But this is where you just slowly keep track of it, but you can see, you can start figuring this out.
Yeah, and you can just.
Okay,
pull
so
out-
hold on a second, let me answer Paul's question. It's like the stuff here. right? So this is again, this is a little hard to read. What it says is, this is always in bits. So compiler guys, like, which bits are we dealing with? Okay, compiler guy, all right. So this is bits 0 through 31. So this X location is added to the Y location, goes into the X destination. And this is the Z plus the W goes into the Y location. This is
The X.
variable B. B's X plus BY goes
Which is
into
128
destination
bits.
Z. This is B, Z, B, W goes into destination W. Does that make sense? This feels weird.
The A and the B
Are two variables
correspond
right here.
to the,
Yeah, so here's your signature. Right, and there's your A and your B. Those are just two full registers.
okay, and then those load up in the struct and the union.
No, those are just that's your whole XYZW. It's 128.
Okay.
Well, on the computer, I can see a little breakpoint right there. You can actually see, yeah, little white space between the two.
Oh, yeah, I can, wait.
So, so for this is, you have to kind of slow down and take your time and kind of go through this. It's a puzzle. And so you're just like, oh, which functions can I use? And it kind of helps you, like, here's arithmetic.
Oh, you're searching.
Right, you can say, oh, I only want the load ones. You're like, load ones. And then there's set functions, there's some other functions in here and you get some choices. Right, so here's load. So like I looked at load SS, I looked at set. Set PS and set PS1 and something like that. So I looked at these. So these are things we could do. Now remember, you gotta test everything. Is this actually fast? Or is there a way to do this in SIMD land? There are functions in this.
And that's faster than initialization.
You have to try it. Because you don't know.
Oh,
Sometimes they're faster, sometimes they're slower.
interesting.
So this is not a slam dunk, just by getting and using, if you get the right answer, doesn't mean it's gonna be faster. This means you got the right answer, right? So it's a puzzle.
So the goal is to use SIMD just wherever we can.
So I saw some of the functions were like loading and storing, and it's just moving data around. Is that
You're gonna need to
we're
do
just
that.
moving data around to do more functions on them, or?
Well, like, you might wanna multiply everything by X. X is not in, it's, do you wanna, maybe you wanna register that has 4 X's,
Yeah.
right? The data only has it in 1 location, but you want it in 4. So you have to do a set function, so it repeats and loads it 4 times. So just play around with the puzzle. It will be obvious when you're starting to do the equations. All the code you're doing here is, obviously you're going to do the proxy, but first you have plenty of work before you get to a proxy land. So, follow matrix, lerps. I do triangle together, so that's probably a good one to start on. I do it completely. So you can kind of see the whole stuff through in the logic there.
That's the one you do in the video?
On the video, yeah, I do triangle there. Let's start doing this stuff. And then when you get to row and column major, you're gonna need proxies to make math a little bit easier.
Both of them or just?
I did it for both.
Oh,
It was 0 work to do it. It's just, what it did though, it removed some temporaries. And so it just moved, but the temporaries made it a little bit faster. To be honest, what happened was the column got faster than the rows. I'm like, what? I'm like going, at first column's really slow, right? So I do proxy, like, cool. So I'm like, how come my column faster than my row? Oh, I got a couple temporaries. Oh, go back to row, put them in proxy. I removed those temporaries. And then they both equaled up at the same time. So this will be a fun one. But please, there's a couple, I want to say roadblocks you're gonna hit on this one. So if you code this week, on it. When we come to class next week, you'll have good questions and we can do that, those questions on there. So remember, SIMD is 10%. It's not a 5% assignment.
Oh, so it's 10%.
Yeah, so there's two assignments that are larger,
Because it was.
TA4
and this one,
and this one. Right, so
An important one.
I almost always give more time on this one, just because it's harder to get it right. But just remember your PA4, don't think like, oh, I got more time, I can blow off more time. You need to get it done.
So this is still due Saturday though? Or is it due?
Well, good,
I'll send out a link on when this is due.
get it done Saturday and then you have extra time.
Well, you're not even grading PA4 till tomorrow, so technically PA4.
I will grade it in order. I will not grade before the time.
Yeah.
Right, so if I'm on Red Bull and I'm hitting with coffee and doing espresso chasers, you know, and I'm in the rain and it's cold and wet and I'm typing faster because I'm freezing, you know, maybe I'll grade all of them at once.
Oh, boy.
But likely I'm probably not. So get, you know, going with this, I think you guys will get there. Remember, no in class next week. Can't emphasize that enough. You come in here, you're gonna be, might as well just turn on the video and watch the Zoom then, I guess. But I would stay at home and watch Zoom there. But the class is still synchronous, so you can ask questions and everything on.
Oh, so you're gonna be like.
Oh, yeah, I'm live. I'm just in my awesome hotel room next to the hospital, so, yeah, you know.
I hope some of these tables are so flimsy.
So,
Well, I think last semester you were teaching out of Europe, I believe.
I had COVID and I failed my health test and I was between hacking out along, I taught the class in there.
Oh, God, you were
And
in
then,
cross country.
last spring, I was having kidney surgery. So I had kidney surgery in the morning, came and taught, and then went back in for a bone marrow tap. So, yeah, no, I'm having medical problems. My mom is the one that I'm worried about, and then my wife has her cancer problems as well. So right now, don't go near my family because some really radioactive. But I'll code it. If I'm still alive here and like, I'll come over here. Like I had pneumonia once and I went there and I'm turning blue, losing oxygen. And and somebody goes, you should go home. And I just made it out the door of the classroom and just started pouring puke all the way to the bathroom. So I will teach until I drop. So, so anyway, any questions? All right, so that's really it, class, but anybody has questions, I can hang on a little bit.
Once I start working, I'll probably.
All right, yeah, so the PA5 was kind of the break, give you a little mental break. And then this is interesting, it's a little different, it's a puzzle. So some people like this one, some people hate this one. And it's not the same person, right? Like, it's very variable. So if you get it, it's kind of a fun thing. And then if you can do this, I think you can sell your skill sets on the open market for a premium.
Yeah, just say, hey, I know.
All right, well, thanks, everybody.
Steer 512 today.
I don't.
I think I'm gonna have to redigest the first part of the video and look at it.